Okay, now let's go through an example problem. It will make it easy for you to follow whatever we have discussed so far. We are designing a simply supported type 1 post tension beam and a total moment of 900 kilonewton meter, and I am assuming sulfide moment is going to be small, MSW is lesser than 30% of your total moment in this case, and height of the beam is restricted to 1000 millimeter. Pre-stress at transfer is 1300 megapascal, at service is 1100 megapascal, and based on the grade of concrete, the allowable compresses are 15 megapascal at transfer and 13 megapascal at service. You see, at transfer slightly higher stresses are allowed, at service you have lower stresses are allowed. Let us say. Now, I am going to use type of pre-stressing stand, and typically this should be 7-wire stand, right. Typically 7-wire stands are common, okay. And nominal diameter is half-inch diameter, and nominal area is 99.3 millimeter square and 1860 megapascal, and modulus of elasticity is 195 gigapascal. Preliminary design. So, again in preliminary design we are trying to get the shape of the cross section and the overall depth. Now, the sulfide to total moment is 11% only, is less than 30%. So, I can take lever arm as 0.5 times the overall depth. The height from architectural conditions, anyway they have given that you cannot go more than 1 meter. So, I am taking maximum height of 1 meter. So, the lever arm is going to be 500 millimeter. Now, I know the height, I know the lever arm. Now, let us calculate the effective pre-stress. What is the moment due to imposed load? Total moment minus sulfide moment. So, it is going to be 900 minus 100, which is going to be 800 kilonewton meter. Now, effective pre-stress is going to be MIL by lever arm. So, 800 by 0.5 is 1600 kilonewton. So, at the end of this, now we calculated what is the effective pre-stress, because in the effective pre-stress calculation we have seen in the preliminary design, if your sulfide moments are lesser, you use only moment due to imposed loads, right. That is what we have done, and we have got. Now, what is the area of pre-stressing steel? Effective pre-stressing force divided by the effective pre-stressing stress. So, which works out to be 1454 millimeter square. So, the number of strands that are required are 14.64. So, we are going to put 15 strands, okay. So, area of one strand is 19.3. So, we are going to put 15 strands of area 1490 millimeter square. Now that we have changed, right. So, exact area is this. So, slightly whatever is available as a round number we are putting it. So, what is the effective pre-stressing now? 1639 kilonewton. Now, we are estimating the concrete section area. So, the area what I need to provide should be from, this is again from preliminary design, we are doing preliminary design, okay. So, you take effective pre-stressing force divided by 50% of FCC allowable, because at this point of time we do not know the eccentricity of the cable and load effects. So, we are saying that due to this application of pre-stressing force, you should have an average stress at the CG should be less than 50% of an allowable value. Quick, this is why it is a preliminary design. So, the area that is required works out to be 273,166 millimeter square. So, the following trial section if you so this is the same section that we have been using in your design right from the beginning. So, I come up with 500 mm flange width, 200 mm flange thickness, BW is 150 mm and width at the bottom also 500 mm. Now, you see, now I have come up with the area, depth, cross section is known, and also I know what is the area of pre-stressing steel, which is 1490 mm square. So, this is at the preliminary design, but I do not know what is the eccentricity, still not known. Where to put this strand, I do not know yet. So, at the end of preliminary design, we come up with the sectional shape and the amount of pre-stressing to be provided, but we do not know what is the eccentricity of the pre-stressing. That is what we are going to calculate, but to do that, now that we have finalized the cross section, let us calculate the section properties. Again, like we did previously, we divide this I section into 3 rectangles, and you know the process, and previously also we did it. So moment of inertia works out to be 3.53 into 10 to the power of 10 millimeter per 4. Area is 290,000 millimeter square. Radius of gyration is I by A, which is basically 121,724 millimeter square. Now let's say kern levels. Okay, what are the kern levels? Again we are doing a type 1 design. So kern zone calculation will help me to quickly establish, right? So KT and KBs, already we have done this as 243.45 millimeter, and these are the properties of the section that we have chosen, right? And pre-stressing steel is this, right? 15 half-inch strands. Okay, so we end up with 1490 millimeter square, and effective pre-stressing force also 1640 we have calculated. Now again at the end of preliminary design, I don't know the eccentricity of the cable. That's what I am going to do it in final design. So let's see, calculate eccentricity. Now for P naught is 1490 times 1300, because FP naught in the problem we have been asked to take 1300. So P naught is this. Now the eccentricity to satisfy this kern 1 problem is 295 millimeter, right? So this we have derived it previously, right? So from the kern zone. Now we have done E. Now we are going to recompute the effective pre-stress and associated variables. Now how do we do that? PE, the effective pre-stressing, is total moment divided by the distance the PE has, or the compression force is moved. This is the lever arm, E plus KT, that we have done. So if you do that 1694, it is coming, right? And since PE is close to the previous estimate of 60, so previously this is from preliminary design, okay, 1640, and what is coming from the final design is also that very close, because anyway in area of pre-stressing steel I cannot put 14 and a half strand, either I put 14 strands or 15 strands, so that is not going to change. Anyway I have to keep 15 strands, which will give me a force of 1694, right? So that means area of pre-stressing field P naught and E will not change, so we need to provide 15 strands only. If this is coming to be much different than what you have calculated your previous estimate PE, then I have to do the iterations until this PE and the previous PE is close, okay. So now this is done. So anyway we have to provide 15 strands of half-inch diameter. Now all these 15 strands I cannot put it in one tendon, so we are going to put 2 tendons in 2 ducts, and then outer diameter I am going to check 50 millimeter. In 50 millimeter diameter duct I am going to put 8 strands, one 8 strands, another one will be 7 strands, and area is going to be 1490 mm square. Then now that eccentricity is also finalized, now I have to go back and check whether it is satisfying the compression stress limits or not. Now transfer, again we have checked, area should be greater than P naught H by FCC allowable YT. If you substitute that, it works out to be 258,266 millimeter square. At service, if you run the same numbers, it should be greater than 252,150. Now which one would you choose? You have to select the area in such a way that both the transfer and service, the compressive stress limits are satisfied. So you have to choose a higher value, which is 258,266. Anyway, if you look at it, what we have provided is 290,000 millimeter square, which is higher than 258. That means if you want, slightly you can reduce the flange width, maybe from 500 to 450. But I don't want to do it, because I wanted to keep it as a nice round numbers, okay, because construction would be easy, right? So but you can, if you want, you can try for 450 mm flange width also, it should work, okay, but I didn't want to do that. So I wanted to keep it 500 by 200, nice section. So this is the section that we have come up with. You see 500 mm flange width, the thickness of the flange is 200, and I put 2 strands in such a way that your average eccentricity is at a distance of 295, okay, from the CG. So E is equal to 295, that we have already calculated. If you go back, E we have calculated as 295, right. So we did this, right. So E you have put as this. So this is the final design. So only in the calculations of E you have to do some iterations, but in this case in the first iteration itself we found the value, because again the provision of area processing stand I have to put it in round numbers, right. So I cannot put it in in decimal, so I have to keep a round number. So it worked out to be good with a P naught of 1937 kilonewton, right. Now this is with respect to design of type 1 section. Now we can define what is called limiting zone for a type 2 member. Again, if you go back in type 2 member, tension stresses are allowed, right, but the tension stresses have to be within certain limit. Tension is allowed in type 2 and type 3. In fact, in type 3 cracks are also allowed, but the crack width will be kept a limit. In type 2 cracks are not allowed, but tension stresses are allowed. In type 2 cracks are not allowed, but tension stresses are allowed, right. So in the limiting zone is the zone for placing the tendon such that the C will always be lying within console. That means I need to know the eccentricity of the cable, maximum and minimum, within which only I have to put the cable, then only my C, both at transfer and at service, will be within console. So that's what we are trying to say. That is a limiting zone. Limiting zone is the zone for placing the CG of the strand. That means eccentricity of the cable. Now for fully pre-stressed member, tension is not allowed. We know that for service conditions, right. For type 2 members, tension stresses are allowed, but no visible cracking is allowed, and transfer C always lie within the kern zone. Also the maximum compressive stress at transfer and service should be within allowable values, right. Now this is what a typical section is. So this is your CGS, and if you see the bottom, this is your maximum eccentricity allowed in each cross section, and this is the minimum eccentricity that is allowed in a cross section. So if I take one section, this value is your E max, E minimum, and this value is your E max. So at any section you will have one E max value and E minimum, within which I have to put the strand, then only the C will always be within kern zone. Okay, that's what we are trying to say. Okay, in type 2 section, now let's calculate a transfer, what happens, right. So this is again sectional analysis, that what we are trying to do. In type 2 section, what is it? A transfer, C will keep going up, but in type 1 C will be at the location of your lower kern point, but in type 2 it need not be, because now I am allowing tension. Now how much tension that is allowing? That will be given by this value. This is a allowable tension value, right. This is an allowable tension value. I should write here. Allowable tension value. Because I am allowing tension, now C need not be at KB, C can be below KB. Now how much distance it is below KB? By distance of E1. And how much distance it has moved away from T? By distance of E2. So you can calculate these numbers to come up with expressions for your limiting zone. So let's see how to do that, right. So this, if you see, the C will not be at KB, but slightly below KB, because I am allowing some tension. If I am not allowing tension, this FCT allowable will become 0, right. So if you see how much that moment that is allowing me to create the tension, which is C into this distance, or in other words, P naught into E1 is a moment that is pushing the tension from 0 to FCT allowable. So the moment divided by moment of inertia times the distance of the fiber will give me the stress. So that moment is what creating this FCT allowable. So this moment My by I will give me the stress. So M here is P naught into E1, because if C is at KB, zero stress. Because C is at a distance E1 from KB, that moment what it is produces C into E1 or nothing but P naught into E1, that is what it is creating this tension. From this I can get what is E1 value, right. Now I know I is equal to AR square, KB the lower component is R square by YT. So I can find an expression for E in terms of FCT allowable in terms of other section parameters as FCT allowable times A into KB by P naught, or you can keep it like this also. Okay. So now what is the maximum eccentricity that is allowable? And you can see here the maximum eccentricity is KB, this distance from we are measuring from here to here. What are the things that is there? KB plus E1 plus E2. Now if we found an expressions for E1, which is this, what is the expression for E2? What is it? It is causing the C from move from T. It is the self-weight moment that is acting. At transfer, you will have moment only self-weight moment. Because the self-weight, now C has moved away from T by a distance of E2. That means the moment that it is moving, that is self-weight moment. So that distance E2 will be nothing but MSW by P naught. So finally I can find an expression for my maximum eccentricity in the form of self-weight moment and the KB value like this. Now we have done the calculation for transfer. Now how about at service? At service what we are saying is the C would have moved further away from CGC and it would be at the top. Now C need not be at KT, but it can be slightly above KT by a distance E3, right. And this is your E minimum eccentricity. Okay. This is a condition for E minimum. Now again we are, because here this FCT allowable is, I am allowing some tension to happen in type 2. Because of that only C can be away from KT at a distance of E3. Now how do we do that? So E minimum in this case, if you look at, we are calculating this distance, how much actually C has moved, that if you know this is your lever arm. So this distance E minimum is nothing but the overall lever arm minus E3 minus KT. That is what we are doing. So KT is a section property. Z I can calculate. How do we calculate? Now the moment that it is acting is MT, total moment. So this is going to be MT divided by effective pre-stressing force, which is P, right. That is your lever arm. Now only thing is E3 I need to calculate. Now what is E3? So C into E3 is the moment that it is creating FCT allowable at the bottom. So I can quickly calculate my E3 as well. Now again the C here will not be at KT, but will be slightly above KT because of FCT allowable, right. So now we got that. Now what is this moment it is creating? C into E3 is creating this FCT allowable, and this, you know, here I should say YB, because the distance is always measured in terms of Y. So YB I put by I. So E3 can be FCT allowable times C by YB, okay. And I is equal to AR square, KT equal to R square by YB. Then I can write P in this form like this, okay. From here I can get minimum expression for your eccentricity from this. If I know total moment, if I know the effective pre-stressing force, if I know this FCT allowable, I can quickly calculate what is the minimum eccentricity for a particular cross section. So the maximum eccentricity comes from transfer condition, the minimum eccentricity comes from service condition. So this is the expression. So quickly we are summarizing. You see that the maximum eccentricity is higher, type 2 has higher values. That means allowable eccentricity is always higher for type 2 and type 3 members than type 1. In fact, in type 3 we may be allowing crack width, so I can still go higher. So the E max and E minimum will be, limits will be higher in type 3 members compared to type 1 and type 2. Type 2 will have higher values than that of type 1.